Hi everybody, and thanks for watching this presentation on a predictive model for predicting sample demand using field supply sales. At the Water Quality Lab, every year thousands of natural water samples are analyzed for things like metals and pesticides, and the lab makes money off of each test that they perform. Lab income depends on the number of samples that are submitted each year, but water quality sampling is also very seasonal. So most of the water quality sampling that happens occurs in the summer months, and this also happens to be the last quarter of the fiscal year. And so usually we are kind of making up for sample income in that last quarter, and so it's always very concerning about, are we going to break even or make back the money that we've already spent previously in the fiscal year, right up until the very end of the fiscal year. So there are a few key tests that make up the majority of sample income, and these are a few of those tests. One of those tests are carbon tests, and measuring carbon in water samples is important because this is a nutrient that's present in natural waters, and it gives you some idea about the health of waters, and so this is a really often requested test. ICP-OES stands for Inductively Coupled Plasma Optical Emission Spectrometer, and that measures metals like sodium, calcium, and magnesium in natural waters, and this gives you an idea about the salinity of the water, which is another important parameter. ICP-MS, Inductively Coupled Plasma Mass Spectrometer, measures trace metals like arsenic and lead in natural waters, and it gives an idea about the environmental and health impacts of different waters. And so those are some 3 tests that we're going to be focusing on for this predictive model because they're important and they're very often requested tests. So over the past, 5 or 6 years, here's a graph of sample requests. The red is ICP-MS requests, the green is the ICP-OES requests, and the blue are carbon. And then the orange line is the total number of requests at the lab. And so you can see that they're pretty, they follow a similar pattern. And you can also see that in the fiscal year 2020, which actually started in October, so we're already almost halfway through, we're only a quarter of the way through the sample demand. So this is sort of illustrating that really 80% of the work happens in the last half of the year, and that at this point in the year, it would be really useful to know what kind of year we're expecting for budgetary purposes. And we can make decisions on things like hiring and purchasing equipment based off of where we are in the sales for this year so far. So is there a way to predict that sample demand earlier in the fiscal year? The lab also sells field supplies, which are used to collect water samples, and these are things like filters and bottles and preservatives that are added to the samples so that they can be shipped back to the lab for analysis. So can we use the sales data for field supplies to predict how many samples the lab will receive? Well, here are some key field supplies that are used to collect the samples for the carbon and metals tests that we were talking about earlier. So nitric acid is a preservative that's added to each metal sample, the ICP-OES and the ICP-MS. The 250 ml plastic bottles, the HDPE bottles, are used to collect metal samples, and then 125 ml amber glass bottles are used to collect carbon samples. So the idea is, can we monitor the sales of these supplies and predict how many samples for these different categories we'll get back at the end, before the end of the fiscal year? So first, kind of looking at total field supply sales by year, and did they kind of correspond with high demand sample years? And thinking back a few slides, you can see that 2016 was a high field supply sales year. It was also a high sample demand year. So this seems like it's going to be a promising model. So the ICP-OES samples which use nitric acid as a preservative and are collected in 250 ml bottles, we can use a linear model, a multilinear model in R to predict this data. So we loaded the data into R, and we used nitric acid and the 250 ml HDPE bottles as predictor variables, and the ICP-OES sample demand as an outcome variable. And using the linear model function in R, we were able to generate a statistically significant model, as demonstrated by that very low p-value on the bottom of the screen. And this model explains about 97% of the data according to the R squared, which means that it's going to be a useful model in future years. The nitric acid variable was significant, so that take a look at that high t value and the low standard error. That's a useful field supply to monitor to predict ICP-OES logins. And so using this mathematical model, you can kind of plug in how many nitric acid and bottle sales, how many quantities you've sold, and you can predict how many samples you might expect to be logged in based off of this data. And so this looks like it's going to be a useful model. Along those same lines, the other metals test, ICP-MS test, can also be predicted using the nitric acid and 250 ml plastic bottle sales. This model is also highly predictive, with the R squared being about 0.97, meaning that it predicts about 97% of the data. This is a significant model with a low p-value, and nitric acid is again one of the stronger predictor variables for this outcome. So based off of those two models, I would say to monitor nitric acid sales would be useful for predicting the metal samples you would expect to see logged into the lab over the course of the summer. Carbon samples can be predicted using the glass bottles that are used to collect those. And this is also a significant model with a low p-value, but the model only explains about 80% of the data. So it has limited practical use, but could still be a good indicator of maybe trending or something like that. And there could be some other field supplies that you could add in to make a multilinear model. In this case, there was only one predictor variable for the outcome variable, and the predictor was the 125 ml amber glass bottles. If you added in maybe something like filters or one of the other preservatives that's used for some of the carbon tests, then the predictive value of this model may increase. So based off of these three models, my recommendations would be for management to monitor nitric acid and glass bottle sales in order to understand what to expect for the sample demand in the summer. And this kind of is different than what is currently done at the lab. Right now, field supply sales in dollars or numbers of orders are what's monitored, and there tends to be talking about like, oh, we're 5% up over last year, but key field supplies may be a better predictor of what to expect for sample income rather than field supply sales dollars themselves. So I would recommend management to change what we're monitoring to predict that and monitor nitric acid and glass bottle sales in order to understand summer sample demand. I think there's also potential for expanding this model using other types of samples that could possibly have a specific field supply as well. So that could be something like using larger glass bottles for the pesticides test, or different preservatives for nutrients like nitrogen or phosphorus. And sometimes we collect pharmaceuticals and there's a specific kit for collecting those. So monitoring those types of field supply sales may also be really useful to expand the model. And maybe there's 3 or 4 key field supplies to monitor that could be used to predict the whole lab's summer sample demand. And with each additional year of data, this model will be improved. So there was field supply sales data from 2014 to present and sample login data as well. So, but more years would be useful as well. Anyway, thank you all for listening.